Because if you want to make gamma ray source or X-ray source, just a source, some source, it's not at all a problem. Sun emits gamma rays. Lightning emits gamma rays, X-rays. Even if you wipe off scotch, it emits X-rays, as has been shown some time ago.
What emits X-rays?
So if you wipe off scotch,
Yeah.
in the process it emits X-rays with very, very low efficiency, but it does. So it's not at all a problem to make gamma rays or X-rays. The real problem comes out if you want to do it efficiently. That means if you want to make a gamma ray burst or a laser which is more efficient than the steam engine, then you need to do some effort in this sense. Okay, then before I go to the constraints as such, let me just remind you that there are some limits on the variability timescales, and if you have a central engine of size G, here, just for example, it's a black hole, but in principle you can imagine some other source, some other type of central engine. This central engine can produce, intrinsically, a variable outflow with the variability timescale, which is just R over C, RG over C. And then if you have a relativistic outflow, if you have two globes with different Lorentz factors, the second one is faster than the first one, the second one catches up with the first one at some distance, which in principle can be much, much larger than RG. But this distance is related to the Lorentz factor of the outflow just because you have the difference in velocities, which is very small in the relativistic case. So if you then calculate this distance as a function of Lorentz factor, and then you take into account Doppler transformation, which makes the observed pulse shorter, gamma squared times shorter, then you again come up with this RG over C. There is nothing you can do about it. Even if you consider a spherical outflow, then geometrical delay will give you just the same RG over C. So variability timescale cannot be shorter than that. In principle, it can be much longer than that. There is no limit of that longest variability timescale, and then I'm coming to an arguable assumption. Perhaps you need to argue with me about that assumption, but I will still insist that probably it's true. If you have relativistic outflow with a good deal of internal energy, then probably dynamical timescale is more or less the same as the light crossing timescale. If all the sound speed, galvanic speed, or whatever you have in this relativistically moving globe, all of them are of the order of the speed of light, it would be very, very surprising if dynamical timescale of the globe is much longer than the light crossing time. So if we agree on that point, then I can continue. Usually, what people try to do with relativistic outflows, as long as we started the story, and started discussing something relativistic, then let's increase Lorentz factor. In many senses, it helps. First, you can move your emitting region further away from the source, and still, because of this Doppler boosting, get short variability. You also, at the same time, moving out and having large Lorentz factor, you also decrease the common photon density. So you alleviate the very, very difficult problem for this powerful source as a problem of internal photon absorption due to photon production. In principle, increasing Lorentz factor can make any source, any arbitrary luminosity, you can make it transparent, not opaque to the photon production. The other point that helps in the sense is that in the common frame you also increase the two-photon absorption threshold.
Excuse me? So here you assume that the source of photons, this is the external photon field measured in a jetless frame?
No. The idea from the very beginning, when they discovered very powerful gamma ray sources, from the very beginning, it was clear that you should avoid two-photon absorption somehow, internal.
Yes,
And if
but
you have
I'm just
intense
wondering-
photon field, you should avoid two-photon absorption, or otherwise you will see a cascade spectrum or even a thermal spectrum thermalized, but
No,
not
I
what you see.
understand. My question is that this W prime, this is the energy density of photon field measured in the jet rays frame,
Yes.
and you assume that this is produced at the jet base, like the accretion disk, hence the transformation on over gamma
No,
square.
these photons are produced, okay, this photon density is inside the emitting region, whatever happens. And at this point, I do not care about the origin of these photons. But in principle, if you say that some photons are produced external to the source, then increasing Lorentz factor doesn't help too much. You cannot decrease harmonic photon density in this way. But if you just have a source which produces some given luminosity, and you want to avoid two-photon absorption, then you probably assume, in the first place, you would assume that all these photons are coming from the jet, and then you can avoid two-photon absorption. If you want to make your life harder, then yes, I agree.
I just don't understand this transformation 1 over gamma square.
Which one?
Yes. What is L? What is gamma square? L is observed luminosity of the photon. You have some source with luminosity L.
Yes, here is the luminosity, the isotropic luminosity, and here is the distance to the emitting region.
Distance from the distance of the emitting region from the source of the photons.
Yes, it's the distance from the central engine.
Okay, so in other words, you put the source of the photons in the very center.
No. Okay, Lukasz, you have the luminosity, but given the luminosity alone, you cannot tell what's the photon density.
Yes.
You need to know at what distance from the source of these photons you are located, or what's the surface which emits these photons, the area of the surface which emits these photons. And the area of the surface is defined by the distance from the source, more or less. Right? Suppose you have a sort of
Okay, but
Spin
maybe you
around
continue. Please continue. I will ask later.
then an arbitrarily large Lorentz factor, you want to assume, cannot be in fact arbitrarily large. As that there is a lower limit which is implied by consideration of two-photon absorption, but there is also an upper limit. For example, if you consider synchrotron radiation, suppose your jet is emitting in synchrotron, then you can make a very simple exercise. Just write several relations. This is the energy of synchrotron photons, observed energy of synchrotron photons at the peak. Gamma prime, small gamma, is typical peak energy of electrons which are emitting in synchrotron. Then suppose this is not an assumption, this is just an arbitrary introduction of arbitrary parameter at 1, which relates the harmonic photon density with the common magnetic field energy density. And you probably, if you have an efficient source, you probably want to make this E1 at least not much smaller than unity. If it's much smaller than unity, then it's not a really efficient source. It can be efficient in terms of transferring energy from radiating particles to the radiation field, but it will not be efficient in terms of transferring Poynting flux energy to the radiation field. If you have E1 much larger than, much smaller than unity, then all the energy is coming out as Poynting flux. Yes.
Why do you assume that you have a strong connection between distance from a source and gamma factor?
I don't assume any connection.
But you
I just take a Lorentz factor which is at the point of emission. Whatever you have.
no, in the previous formula.
Well, I think the question is very first transparent. Is that the distance is proportional to gamma square?
Yeah.
No, this is previous one.
No.
This one, look here.
Oh, this one.
Yeah.
It's a minimum distance when you have collision. You cannot have collision of two blocks at a distance smaller than that. Just not enough time for the solar.
There is also
for
an
to
assumption
catch up.
that delta gamma.
It's just estimation for the low limit.
Yeah, more or less. Yeah.
Assuming
It has
the
the
difference.
yes, yeah, the difference is small. So it sent to shells with delta gamma for order of gamma, and then the collision takes place at gamma squared times.
No, I understand it. Just you could have slow acceleration.
It doesn't come make sense.
But assuming it's here, it's somewhat specific model. In terms
No,
of
not really.
sense.
Okay. Probably there is some subtle point here is that this gamma is something average between the Lorentz factor of slower block and Lorentz factor of faster block. It's not the smallest gamma, it's not the largest gamma, it's something average. If you have variability in gamma very large, say Lorentz factor varies from basically from unity to some large Lorentz factor, then this gamma would be just unity. In this case.
Yeah, but
But if
this
you're
picture
simply-
is something like colliding, it catch up and collide. So that's why we get this scaling.
Yes, yes.
Yeah.
So I basically assume that whatever is expelled, it expelled at relativistic velocity. Some parts are moving faster, some parts are moving slower,
Sure.
but they're anyway they are relativistic. That's what I assume. So it's not a relation of Lorentz factor to distance; it's the minimal distance you need for the collision. Then you have also radiation efficiency, which is the amount of energy electron can radiate during dynamical time scale. If electrons move fast, then this eta 2. It's the ratio of dynamical time scale to the radiation time scale, basically. So if electrons cool fast, then eta 2 is much larger than unity. If electrons cool slow, then eta 2 becomes much less than unity.
Dynamical, you call the expansion time scale?
More or less, yes. So to have a good efficient source, you need both eta1 and eta2 not much smaller than unity. The product of them cannot be much smaller than unity, or otherwise you will observe just some small part of total energy injection from the source, and somehow this energy should dissipate anyway. Create some problem. It was not radiated. Okay, then this is just a relation of common photon density with their isotropic luminosity. Then you do a simple exercise which I can in principle reproduce on the blackboard if you want it. I do the simple exercise substituting gamma prime and b from first two expressions in the third one. And what you get from there is the upper limit on the Lorentz factor. It's easy to understand why it comes out. Because if you have a larger and larger Lorentz factor, you also decrease the common energy density in magnetic field, in radiation field, in whatever. So the cooling time scale increases if you increase the Lorentz factor. But the variability time scale or dynamical time scale decreases, it increases in a much slower way. So to say so. They both increase with the increasing Lorentz factor, but the common energy density increases much faster. Decreases much faster. So
What this gamma means?
this gamma means that if you have a jet with a Lorentz factor larger than this, it cannot be.
But you're arguing something two components and slower one and the rapid one and collide each other, and what's this?
This is something average. Yes,
It's
I agree. If you have, no, it's not even the Lorentz factor. You can average it appropriately, but if you have variations of Lorentz factor not in a very large magnitude, say from 1/2 of typical gamma to 2 times typical gamma, for example, then this is just the average between the two. If you have very large variations, then I cannot tell you. Then it depends on how much mass is ejected with slow Lorentz factor,
Exactly.
how much mass is injected. with
That's
large
why
Lorentz
that's
factor.
one.
Yes.
It should depend on detail model.
Yes. true, except that in fact you have a lower limit on the Lorentz factor if you assume that there are some blobs, some portions of the jet which are moving at slow speed, but small Lorentz factor. Then for these portions of the jet, two-photon absorption will come into place. And you want to avoid this. So that the lower Lorentz factor is still limited. It cannot be just units. You have slower portions of the jet, you have faster portions of the jet. For the faster portions of the jet, more or less you have this limit on the Lorentz factor, let's say. Now this gamma is average, it is smaller than the largest gamma in the jet. Then the largest gamma in the jet should obey this more or less also. But then you also have limits on the Lorentz factor of slower portions of the jet, because these are the most efficient radiators. The slower portions of the jet are missing the most fraction of their energy.
But obviously, selecting the first guy is important part. Yeah? First guy is supposed to have a larger part of energy.
In terms of two-photon absorptions, the slower guys are the most important. The slower guys determine the two-photon absorption. They basically
But in
keep
terms
radiation
of
fields in them.
efficiency, that issue. If we discussing efficiency, it's you're arguing some kind of efficiency argument. So.
Yes. At this point, yes, but the argument about two-photon absorption is still in place. It has not gone. You still have some lower limits on the Lorentz factor derived from that. I just don't come into this because it's more or less well known. But you have some lower limit on the Lorentz factor. You cannot go lower than that because you have problems with two-photon absorption.
Maybe discuss later.
Sorry, the paper you cite, Biggerman, Fabian, is that about the variability, fast variability? Is the one?
Yeah.
Okay.
Maybe there are several papers about that.
Pardon?
Maybe there are several papers about
No,
this.
just to remind me.
Yeah, but this one, yes, it's about rapidly variable.
And
sources.
this gamma that you derive, this thing after leading to gamma, well, it applies to low luminosity sources. I mean, in this formula you have that it's quite strong. I mean, compared to the others.
Why? It applies to you just plug in the luminosity you have.
Just pump the luminosity of gamma reverse there, and
Yes. For gamma ray burst, it's yes, thank you. For gamma ray burst, if you plug in the luminosity of gamma ray burst, okay, you have also different variability time scale. Here it's in units of. Oops. Very nice. That's it.
Quality so long in one step.
Exactly.
Source searching.
And?
Do you have the system isolated?
Very nice. Okay. This is the variability time scale in units of 1,000 seconds. In gamma ray burst, you have faster variability. You plug in faster variability. You plug in larger luminosity. What you get is something like 6,000. This is the upper limit. So for gamma ray burst, it's not a limit at all. You are most certainly below that limit. Yeah, but for AJNs, it's a limit because there are some models which are considered just with Lorentz factor of 100. And cannot.
This is epsilon 6, and what units is that?
It's the peak energy of synchronous photons in units of 10 to 6 electron volts, 1 unit.
10 to 6 what?
Electron volts.
Electron volts.
1 unit.
Mhm.
So if you go to lower peak energies, like for GV blazers, you have peak energies below 1 keV more or less, then this upper limit is even lower. Okay, but the dependence is not that strong. It's somewhat lower, but not that much. Okay, then let me come to two-photon absorption once again. And I want to make an observation that if you compare the cross-section for two-photon absorption, gamma-gamma to E plus E minus, and for compound scattering of electrons, gamma electron to gamma electron, then if the Kleinian limit in the limit of large energies, the cross-section for scattering is smaller than the cross-section for two-photon per production, 2 times smaller. Two-photon per production has larger cross-section. What does it mean? Suppose we have a source with some photon field. Let's calculate the two-photon, the optical depth for two-photon absorption. This is sigma gamma gamma times the number density of photons times the size of the source. And then let's calculate the inverse component energy losses in the Kleinian region. Then it's just this one, and here enters the Thomson cross-section for electron-proton interaction, and basically the same number density of photons. Because the largest cross-section for Compton scattering is at the same energy where is the largest cross-section for gamma-gamma interaction. So it's the same photons that are Compton scattered and that are producing two-photon opacity. Then, if you take into account this...
But I mean, you can have softer photons also.
Yes.
It depends on the spectrum of your
Right,
photon
right.
field, right?
Let's assume that the scattering is in the Kleinian region. Just assume. What we have out of this is that we plug in the ratio of sigma gamma gamma to sigma e gamma, and then we just have independent estimate on the how gamma gamma optical depth for two-photon absorption. It's larger than 2 times this ratio, and this ratio is 2. Even more than that, because we have in the Kleinian region, we have if you observe the photons and the observed photons have 2 times less energy, and they interact more efficiently with high energies. So this should be much larger than unity anyway. If you assume that the scattering is in the Kleinian region, it immediately comes out that you have an intrinsically opaque source of high energy photons. If you want to get them out, you need to get rid of this assumption. An efficient source of high energy upscattered gamma rays must be in Thomson region. And then, as you said, you have low energy photons which produce inverse component cooling, but do not produce two-photon absorption. This is more or less clear, I guess. You want to have an efficient source of high energy photons, go to Thomson region. If you don't want it, you may do whatever you like.
And then, so if you have just large absorption column density for high production, gamma gamma absorption, so who cares? You just go to low energies, it's still right. You get a cascade or whatever. So it should be still
Yes,
fine.
but these photons do not come out. They
At
come
some
out at
point.
low energies.
Yes, okay.
Right. But let's assume you want to have
At a given energy, you want to have something at a given energy.
at any energy, because if you go through cascade, you lose some energy through synchrotron as you cascade down. And I would even probably say that there is another argument against cascading. In most cases, what you observe from the sources, it doesn't look like cascade spectrum. Cascade spectrum is just flat. The new field is just flat. It's not what we see. So probably it's not heavy cascading. It's not fully developed cascade at least. That means the optical depth. If it's large, then it's not much larger than unity. Otherwise, you have fully developed cascade with flat spectrum. That's it. Then let's suppose that we want to have a source which produces high energy photons through self-compound. So it's simple self-compound mode. Then remember that we must be in the Thomson region to be efficient. Then the peak energy of the inverse compound photons is very simple. Just gamma prime square times larger than the peak energy of synchronous photons. Once again, relation between the radiation energy density and the magnetic field energy density. Radiation efficiency is defined as the cooling is the ratio of the dynamical time scale to the cooling time scale. And if you have predominance of radiation field, just if E21 is larger than unity, then you have to add this additional factor. I will skip it later because it really doesn't change the answer too much, but it makes expressions more heavy. And then the same exercise. We plug gamma prime and B from two equations into the third one, and we get again the upper limit for the Lorentz factor. And in this case, it is much more strict. For active galactic nuclei, it's basically gamma less than 20 for the typical parameters. And then it becomes already stressing because we know that active galactic nuclei probably do have Lorentz factor about 10 or 20. So they're probably operating closer to the limit. You cannot move the Lorentz factor anywhere.
I should say for external compton, this limit don't apply there. It's for synchronous.
Yes, this is for
high gamma external anisotropic.
Yes, I will come to external compton later. And again, for gamma ray bursts, you can do the same exercise. It's not really strict, but it becomes a sort of limit. It's below 1,400, something like that. The Lorentz factor should be. Okay, there are some models of gamma ray bursts which are considered Lorentz factors up to 1,000 something. So it's already a limit. But then, this is a limit if you assume that the condition of gamma ray burst is inverse Hom condition, you observe, which is probably not the case. I would consider this very unlikely, but if you want to do a model like this, then you have some limit. Oh, and then I will probably need to explain why I write here 21 and not 20. And this is because all the dependencies here are very big. Look at the powers. All the dependencies are very big. So it's really a strict limit. If you want to make a Lorentz factor, say 40 instead of 21, you will need to make efficiencies very low. Sometimes 1% or so. It's really a good limit. It's not that you can increase Lorentz factor several times above the limit and you still have some appreciable efficiency. It's not like that. Efficiency drops very rapidly. Yes, and this is to explain once again how it works. You have dependence of the efficiency, say, which is the ratio of the poietic flux to the radiation flux, and we have the cooling efficiency, H2. As you increase Lorentz factor, this one moves up, this one moves down, but much faster. So the crossing point, where you have the largest product of the two, the crossing point moves down and to the left. Eventually, with some Lorentz factor sufficiently high, you just go below unity. That's more or less. And yes, if you still haven't noticed that E21 is basically its quantum Y parameter. It's different by some geometrical factor from the quantum Y parameter, but it's more or less the same. Then let me come to the external quantum radiation model. Then you don't have limitations from SOC model, but you may derive some limits from a very simple assumption that the occupation number of photon field, external photon field, cannot be larger than the Planck spectrum. Now it's more or less obvious assumption, or otherwise you have something like laser, which is probably not true. And I would even say that most likely, because you have lines as you know, because you do observe lines, that probably means that the occupation numbers are much lower than the Planck spectrum.
For what temperature?
For
what temperature? I mean,
for any temperature. Just take the Planck spectrum, and I will come to that. I will come to that in just later. But at any given energy, let's assume that the occupation number is less than in the Planck spectrum, it's some temperature. I will then discuss later what temperature you can take. Oh, I can come. I think I can come up with at the time. I think I can come to that. If we increase temperature, we increase the maximum possible occupation numbers for a given energy as temperature to the first power. But then we cannot increase temperature too high, because if it becomes too high, then it means that the most of the photons are located at large energies, and if there are such large energies that they are scattered of electrons in the Clandestine region, you are done. It must be in the Thomson region. So the temperature is limited. It cannot be infinite. It's limited by this assumption that you are in the Thomson region. So compensation in the Thomson region means that the typical energy of photons is less than this. This is again the typical Lorentz factor of the radiation electrons in the common frame. And then you have, if you want to have good radiation efficiency, that means cool and sufficiently low, it implies that the occupation numbers must be sufficiently high. In the case of SSC, it must be higher than that. In the case of external radiation component, it must be higher than that. And the basic difference is the dependence of the bulk Lorentz factor. And it's clear why it depends in that way. Because for external quantization in the common frame, photons occupy the angle, solid angle of 4 pi over gamma squared. If you have isotropic in the left frame, initial them in the common frame, it occupies solid angle 1 over gamma squared. That means you need for a given radiation efficiency, you need larger occupation numbers. And then occupation number must be larger than that, and it must be less than in the Planck spectrum, and it gives you a lower limit on the Lorentz factor. And this lower limit is not really terrific if you have a high energy peak at say GeV energies. Or basically, all you need is that your sources is at least mildly reduced. If you go to TeV energies, then it becomes stressing, especially for external radiation component. It depends on the peak energy of high energy radiation as this energy 1.5 power, and that means if you take say 10 TeV source, it should have Lorentz factor about 100 at least. If you want to make a 10 TeV source as external photon source, if it is an SSC source, then 100 is much weaker. It's more or less acceptable, I would say. And some of TeV blazers they are actually 10 TeV blazers, not just TeV blazers. I doubt that you can really make a good external radiation quantum model for this high peak TeV blazers, because you need too large Lorentz factor. And even assuming that the photon density is Planck, the local photon density, and it's less than Planck, then you have still higher than the Lorentz factor.
Is it important that your 10 TeV photons are not at the peak of the distribution, because the peak might be at 10 GeV and the 10 TeV is just the tail?
Well, it's a question of efficiency. Basically, if the ratio of the fluence at 10 TeV at the peak is not that big, then it's not really important. If most of the energy is radiated at, say, 10 GeV, and at 10 TeV you have 1% of the energy, then it will be relaxed.
Because those objects which we see on TVs, they have soft spectra, right? Except there are a few examples that we talk here about that might have even harder spectra. Even higher than TVs.
If they have very, very soft spectra, then it's not really a big deal.
Okay.
Yes. Okay, then let me come to distinction between TeV sources and synchrotron sources. If you have an inefficient source, and for this inefficient source, we plot dependence of the overall efficiency as a function of the component magnetic field strength, this will be just a single peak where the peak is located more or less at the point where equal 1 is equal to unity. But then we want something else. We want an efficient source. There is a big window in the parameter space where the efficiency is close to unity. And then we have two boundaries. Above this boundary, E2 is larger than unity. Above this boundary is E2 is larger than unity. And in between, the product of the two is more or less equal to unity. We also have some specific magnetic field strength, which is defined in such a way that if the magnetic field is equal to this big Kn of the machine, then the synchrotron photons produced by electrons in this magnetic field will be just the limit of machine regime for inverse component scattering for the same electrons. If you move to lower magnetic fields for a given peak energy of synchrotron, this means that you have more energetic electrons and then the scattering is in the machine regime. If you go to larger magnetic field, then the scattering for a given synchrotron energy moves in the close energy. And here you have transparent for two photon absorption sources. Here you have opaque for two photon absorption sources. So basically you can put efficient synchrotron sources like GRBs, I would presume, you can put here in this diagram, and efficient TV sources you can put right here.
So if GRBs are compensated, where do you put them?
Then it should be put in the same place as TV sources for different parameters. I wouldn't really believe that because if the observed radiation, imaging radiation is produced by inverse compound, you would probably expect another cascade of inverse compound, which must be higher than the first one. It will be still in the Thomson regime. It will be higher than the first one, and then.
But it can be inclination. Yeah.
It will not be if you plug the typical parameters. It will be still in the Thomson.
Yeah, okay, there is one difference in gamma ray burst because, for example, in a fireball you start with many photons right from the beginning, from your inner parts, and these photons are carried with your flow. So it's essentially an extra source of soft photons, isotropic in the comoving frame, that can cool your particles, and they are not synchrotron produced. So you can carry with you, essentially with your jet.
Why it's an external source?
No, it is.
It's carried away with the flow unless you have the flow.
But you don't have to rely on synchrotron photons as a source.
Right, but you cannot carry photons with the flow if it's transparent in the Thomson spectrum.
So
if it is not, then
up to the photos, up to optical depths of order of unity, actually the radiation in the fireball accelerates the flow, so they're fully coupled. And
so you want to put your emitting region right at the place.
No, actually further out, because of the relativistic nature of the flow, they coexist the two.
Yes, but then it's not as a problem.
Yeah, you have to take this into account. Let us say that we do have this extra soft photons. Yeah, you have to include it.
Yeah, I mean it's the same. It's basically the same, but then
it complicates the analysis. I mean, I just in this case.
Not really. I can tell you the difference right now. Here, you wouldn't have gamma square of the flow. Instead of gamma square of the flow, you will have a square of the ratio of the Lorentz factor, the bulk Lorentz factor of the. You will have square of the ratio of radius of the emitting region to the photosphere radius. Yes, but then I would say for gamma ray bursts, it's not really a big deal. And negative galactic nuclei. It's difficult to imagine that you have some photons carried with the flow.
No, I would just say for gamma ray bursts, not for
Okay. So if you believe that gamma ray bursts are produced by synchronous radiation, I do believe, I don't know about you, but yes, this is my belief. If it's produced by synchronous radiation, then it should be radiatively efficient first, and it should be opaque to the inverse Compton radiation. And this leads to the condition that E must be less than E Klein Machina. And if you plug in the expression from E Klein Machina, you just get, it's very strange that almost every dependence, every unknown dependence cancels out in this expression, but you have just an upper limit on the variability time scale. The variability time scale cannot be less than something, and the something is this expression where you have no dependence on the unknown parameters like Lorentz factor or flow. It's dependent on the isotropic luminosity, which you know, and on the peak energy, which you also know, it's measurable. I would say that it probably explains why X-ray flashes are less luminous than gamma ray bursts for a given variability time scale. What happens if you go below this upper this lower limit? Then what happens is that you go in the region where B is less than B Klein Machine, and then you produce a lot of inverse Compton photons which are not internally absorbed. You should see inverse Compton peak, which should be pretty large in case of gamma ray bursts. If you want to get rid of this inverse Compton peak, you should go in the region where inverse Compton photons are internally absorbed. You cannot really rely on the intergalactic absorption by extragalactic extragalactic light sources. Well, at least until you go above, say, 100 GeV, you cannot rely on this absorption.
I'm
below
confused.
100
What
GeV
you
must
say
be
about
absorbed.
the X-ray,
Hmm?
X-ray flashes? Could you repeat?
If you plug in a lower peak energy for X-ray flashes, it's not at 1 MeV, it's at lower energy. This limit moves to larger time scale. So the X-ray flash, with the same luminosity, it must be less variable. It should have large variability time scale.
And it is.
So,
This is what I'm saying.
so what does it mean?
Probably it's just a manifestation of this relation. It's not something specific to X-ray flashes. But I would presume if X-ray flashes and gamma ray bursts are produced by the same physical engine, then this physical engine probably doesn't know about our intentions to have efficient outflow or inefficient outflow. It just produces variability of its own. And then the variability time scale is given by the physical engine. And for a given variability time scale, if you have sufficiently low peak energy, it probably go below this lower limit. And then it means that X-ray flashes probably are good candidates for high energy emission.
Good what, sorry?
Good candidates for high energy emission.
In
For,
inverse
for
Compton?
having inverse Compton peak. It's good to check if there are any detections.
Okay. It was proposed, indeed, that the quantization of X-ray flashes would produce high energy, extremely high energy. That was not
Should be.
detected in. Yeah.
Yes, it should be.
But sorry, to make the point clear, I still missed something. You're basically saying that the X-ray flashes and let's say gamma ray emission prompt, what we call prompt emission of gamma ray burst, according to this picture, are both produced by the same mechanism, right?
I don't know. I'm saying if they are produced by the same mechanism.
Well, it can be also a consequence of this. If the radiative efficiency is the same and is a property of the emission mechanism, the prompt emission and the X-ray flares, X-ray flashes in gamma ray burst scales with. Every time I make a question, it's switching off.
Yes, yes.
Either that I'm too long in making my questions. The communication from my voices, which is off. You have to shut down on my voice tones, right?
Yes, probably. I don't know how to do it by software, but somehow it happens, yeah.
Okay, so I stop here, maybe it's better because
No, go on.
no, it was just a consideration of the fact that I think it's reasonable.
So what's your point?
My question was, are you saying that with this argument, could you say or could you conclude that this is an argument supporting the fact that X-ray flashes are produced by the same mechanism that produces prompt emission?
No, I cannot. I can only say that if they are produced by the same mechanism, I would expect that X-ray flashes would produce some external, some inverse Compton radiation with high,
Which is not
high
detected
energy.
yet,
Yes.
maybe.
Yes.
But the variability that you predict is
if not,
indeed observed, the
if not-
luminosity is that one, and the peak energy scales.
yes, but if not, if it's not observed, then it doesn't produce this high energy radiation by inverse Compton, then individually it means that X-ray flashes are produced with larger internal variability time scale. You cannot probably do it with the same central engine, I would guess. And it probably, vice versa, it's an argument against the same origin.
But actually, if you analyze temporal profile of GLBs, it containing very different timescales.
Yes, the X-ray flashes are less
Yes,
variable.
I'm talking about the
Yes, that's true. I don't know why. One reason can be that just faster variability we cannot see it because at this point, where the source is highly variable, all the energy is going into a reverse compound. This may be one reason. Another reason is that it's intrinsic to the source. The central engine is less variable for some reason. But you can easily distinguish between the two opportunities. Just look at the high energy emission. If it's not there, then there is only one option. I don't know whether you can claim based on the present state data, or whether you can claim that there is no high energy emission from X-ray flashes. I just don't know whether it's possible to claim this.
There are no data.
Yes, but you have some X-ray flashes which happened since the launch of Fermi. And then, I guess,
Well, there is something like 50% of burst having X-ray flashes somehow at a few thousand seconds after the burst. I mean, X-ray flashes are not uncommon, I would say. The problem is that you should observe the same burst with something that allows you to detect the X-ray flash, so swift, and with an high energy detector like Fermi, they should be contemporaneous, they should follow the light curve up to 1,000 seconds, and so if you have the quantization of the X-ray flash radiation to the GeV energy, maybe you detect it if it is bright enough. So somehow a lot of this. But yes, I mean,
okay.
Let's continue.
So we have to look for the data, I guess, or to wait for the data. And well, one extra unit we can put on the gamma ray burst central engines. Just from this limit on the variability time scale, again, I'm putting forward a statement that the source itself, the central engine, doesn't know about our intentions. So it produces variability of its own. And then if you assume that the lowest possible variability time scale is just RG over C, then you have a lower limit on the mass of the central black hole, which is 3 masses of Sun. Well, it's not a big deal. It becomes a bit more restrictive if you go to large isotropic luminosities. Then it becomes something like several tens of solar masses. But I would say it's still acceptable for stellar or for supernova origin of gamma ray bursts.
Actually,
what
question.
happens if you? What happens? Sorry.
Yeah, okay, it's going on.
It's acceptable, even if you plug, say, 10 to 40.
No. I mean, if you
54.
instead increase the energy, it's you're going down quite a bit.
If I decrease energy, yes.
If you increase the peak energy, if you put it at GeV,
not that many bursts with high peak energy. There are some probably, I don't know, but the most of them are.
I suppose in the future there will
Yeah,
be
maybe,
bursts that
maybe
will-
for such a source that there is no.
Yeah, actually, the variability is determined by light crossing time, so that's a question. You say that's okay. So our usual assumption is source size determining variability time, but these days AGN showing very rapid variability, and it's smaller than light crossing time of black hole.
Well, it's not that clear that it's more than the light crossing time. Let me go to AGNs then.
Okay.
If you're asking
Sure.
for that. This is the last point of my talk. So sorry for having a bit long. Yeah. So a good TV laser must be something opposite to a good gamma ray burst. It must be radiatively efficient as well, but it must be also transparent to produce high energy radiation. And that means that theta 1 at the point where B equals to B by machine must be larger than unity. And then this inequality you can treat in two ways. Unlike gamma ray burst, where magically no Lorentz factor disappears from the final answer, here it does not. So you can treat the answer in two ways. One way is to put here, but here it becomes a lower limit on the variability time, an upper limit on the variability time scale, which is dependent on the Lorentz factor of the jet, and the dependence is very rapid. So it's not really a big limit. And you can also put a limit on the Lorentz factor of the jet, which becomes an independent upper limit. It's independent of what I have said from efficiency considerations before. And this upper limit is and once again, this is in the case of SSC model for high energy radiation. If its external component doesn't apply, I have presented some arguments that TV blazers are probably not produced by external component because then you need two high Lorentz factor. Well, it depends on your point of view. From your point of view, maybe not too large if you have a Lorentz factor of several hundred in an AGN, or maybe it's acceptable for you, but it's a bit stressing for me. And then, again, a byproduct from these limits is the upper limit on the size of the black hole in a TV blazer. Yeah, it's 10 to the 17, but do not believe this number because you have gamma to the 6 in the denominator. If you plug gamma 10, then it's not a big deal. Basically, all supermassive black holes are below that limit. But if you plug, say, gamma 100, then it's a big deal. It becomes too low. So probably it's once again probably it's an argument that first the Lorentz factor is not that too high in TV blazers, and second, as you can see from this inequality, it's easy to make a TV blazer out of a small supermassive black hole than out of a large one. And maybe this explains why all TV sources seems to be not so massive black holes.
I think it's rather the opposite. The TVB lux have the most massive black holes. That was tough. Like Yuri, Wu, and then other people when they estimated masses of the black holes.
From
TVB
balance
lux,
properties.
yes, and they are the most massive black holes. 10 to 9 or so.
Well, you can probably find the reference, have a look at that.
Oh yeah, yeah. Like in
Oh,
general, every paper about
Yeah.
BLX. The BLX.
All I know is that Mercurians, which are very well-known sources of TV radiation, and which are rapidly variable sources, actually, they are not very massive.
In a sense, what are the masses of the black holes measured?
In Mercurians, well, they are thought to be in the range of 10 to 8 solar masses.
Yeah, all ATN are between 10 to 8 and 10 to 3, few times 10 to 9. Right?
Yeah, so all I'm saying is it's easier to make a TV source out of a small black hole. But yeah. it's not such dramatic. You have gamma to the 6, so just adjusting gamma, making a bit less, you can go to high masses. But it tells you that you cannot make Lorentz factor too high. Once again, it's just several times you have the same result, but the Lorentz factor cannot be too high. Several times at most. Or the other way around. If you have external content, the Lorentz factor must be very high. Then it depends on you what you will prefer. To have very high Lorentz factor with external content, or more or less moderate Lorentz factor with self-content.
Can I ask you, so all these constraints apply for the internal shock scenario? Because you scale like gamma squared the distance of the emission region, right?
Well, not really, because what you plug in is the distance from the central engine to the emitting region.
Which is gamma squared. Gamma squared times
Yes, that gives you the minimal distance, right? And if you go to a larger distance, I would say it's still applicable to that, but then the dynamical time scale will not be the time scale of the black hole. It will instead be, the distance to the external shock divided by gamma squared. If you go in the common frame, then your dynamical time scale becomes distance to the source divided by gamma due to Lorentz contraction divided by C. And if you do Lorentz transformation accounting for Doppler factor in your lab frame, you get this gamma squared again. Basically it's the same, but then there is no relation between intrinsic time scale of the central engine and the time scale of the emitting region. They are different.
Yes, I mean all the scaling that we propose, they are strictly for the internal shock scenario.
No. I would say this one, yes, this one is for internal shock scenario, where you have relation between variability time scale and the size of the central engine. But this one is independent on this. It also applies for external shock. Then it basically gives you that there is an upper limit on the size of the external shock, because there is an upper limit on the variability time scale. You can twist these limits in either way you like. It's not very much dependent on the model. I would say that the only dependence is that here I imply that emission is self-content. I wouldn't say that there is anything else here.
Can you show me the limit on the mass of the black hole for gamma reverse?
This is a blazer.
Blazer.
This is also for internal shocks scenario.
Yes. And once again, this limit is for any scenario you like. When you come to relation between variability time scale and the mass of the central engine, then of course you
have to assume.
imply that it's an internal shocks. Yes.
I don't know very much about AGN or black holes, but so if you have an AGN with 10 to the black hole size 10 to the 8, 9, so on. Perhaps could it be that it's not a single object, but it could be an extended region of objects that are not haven't merged, and that your emission, I mean, the entire active nucleus is really a lot bigger than you would think it to be in case of a single black hole. So basically, you'll have a lot of.
I get your point, but all I can say in this relation that probably the assumption that you do not have a single central engine, instead you have a cluster of them.
An extended cluster.
It seems that it will contradict fast variability you observe from some AGNs.
Okay.
In Markarians, you see, in TVs, you see variability on the minute time scale, basically 10 minute time scale.
But that's provided that this variability springs from the launching.
Yes. Can you
make it
propose
vary
any
in other
different
ways?
explanation for that, for past life?
It could be an external effect.
Yes, it could be, but then, once again, we have to assume that, for example, there are some models like you have an external shock going into clumping medium where clumps are very, very small, so the dynamical time scale of a single clump produces your given, this given shock variability time scale, but then you need many, many small clumps. Because they are small, you need many of them. If you have many clumps, then probably all you see is that all these peaks just merge together. You see a sort of smooth flat curve. This is what I would suspect. But in principle, by fine-tuning parameters, you can probably explain it this way.
Those recent jet in jet thing will allow you something variable and it's not related to centralized jet activity.
That's it? That was the final slide? Okay, let's thank Evgeny. We had a lot of questions on the way.
Is it correct if here you think about the limit instead of the mass of the black hole given by stellar evolution? You cannot assume also that the luminosity is standard for all the gamma ray bursts 10 to the 51 as you used here. You cannot move the energy. I mean, you
This is
derive-
observed luminosity.
Yeah, indeed.
Isotropic.
This is isotropic luminosity.
Okay.
Right. So in principle, you can change it by changing the solid angle.
Okay.
Of the jet.
Sorry. Yeah. It's isotropic. It's a reasonable value. It's what you observe. I mean, there is a spread. Okay, then have a factor of even 10 lower luminosity or higher.
But you have
But-
three orders of magnitude higher.
Okay, assume that it is this one. You can set a limit to the peak energy with this argument, assuming that the minimum mass of a black hole that you can form from a star is a factor of 2 lower. I mean, the peak energy shouldn't be larger than 10 MeV or something like that.
Or otherwise, you will have an inefficient gamma ray burst. You can still have it, but it will be inefficient. It can be inefficient in two ways. Either inefficiently radiating, that means most of the energy is coming out as pointing flux and dissipates somehow at large distances, so we do not see it, maybe. Another option is that it is inefficient in MeV energy range because it is too efficient in, say, TV energy range. Produces very, very high inverse component. But it seems that it's not what we see from further results. Yeah. So this probably, if you put it in this way though, the gamma ray bursts which are peaked at lower energies should be inefficient, more inefficient than those which are peaked at high energy. And this will probably give you some relation like luminosity to peak energy,
Indeed.
which we do see.
In fact, if you really
It's unbelievable.